And here we have some calculations and conceptual questions where we're thinking about changes of phase or state. So ice melts at zero without an increase in temperature because heat flows from the surroundings to the ice. Obviously, I didn't say that very well, but the idea is when something is melting, the surroundings would be hotter. We do have a difference in temperature and we have a flow of heat in. But that ice isn't instantly going to go up to water at 20. It has to totally melt and turn into water at zero. And during that process, we are breaking the intermolecular attractions, in this case, specifically the hydrogen bonds between the water molecules, and increasing the potential energy of those particles. They aren't actually moving faster, they're just a little bit further apart and moving more freely. So even as we describe the particles of water in ice, it's a very structured arrangement. There we go, crystal arrangement of those particles where they are very close together in a specific way where the bonds or the attractions can be made. When it's a liquid state, they're moving a little bit different, and that freedom of motion is a result of more energy. The second one is what we might refer to as a heating curve calculation, where we have a pure substance at one temperature going to that same pure substance at another temperature, but in a different state. Anytime we're calculating heat for a temperature change, we would use Q equals mc delta T. Anytime we are using the heat for a change in phase or state, the equation is Q equals m delta H. The delta H is either the heat of fusion, the heat of vaporization, or the heat of sublimation, and it has the unit of either joules per gram or often joules per mole. In this case, or in the notes case, I gave it in joules per gram. So you would need to know this value. It would have to be given. We had it in the notes, this value and this value in order to do this problem. The other thing that would be important is recognizing that water boils at exactly 100. So we have liquid water and we have steam. So what we do is we take our liquid water that's really cold, 3 degrees Celsius, we heat it up, but the hottest that liquid water can be is 100. So it takes 66,000 joules of energy to get our water ready to boil. But then it takes an enormous amount of energy to get those particles moving far enough from one another. So to spread those out or to boil. And if you've boiled water, you know that it gets hot way before it boils. Because it takes a huge amount of energy. And we're not just talking about it starting to boil, we're talking about all of it boiling. So that's why we have this 370,000 joules of energy there. But then once it has boiled, if we take our steam that is now at 100 and we warm it up to 126, the temperature is increased by another 26 degrees, and we can see how much more heat is there. And then we sum all of these up. Sometimes with constants and temperature changes and subtractions and all that. And then in addition, sig figs are a little bit weird, but we do our best. And then here, C asks about the final temperature when a piece of ice at -15 is placed into water at 20. This is a little bit of a tricky problem that may require some guessing and checking or some trial and error to figure out. But what's going to happen is the water we know will cool down. So right here, I have the mass, the specific heat, and the temperature change of the water accounted for. Because the water is 8 times more water than we have ice, we could maybe guess that that ice is going to totally melt. And in this case, it does. So what happens here is a lot. My ice goes from -15 up to 0. That is mc delta T right there. The mass, the specific heat of solid water, and then I end the highest temperature the ice gets to is 0 after starting at -15. But then that ice also has to melt. So it also has to undergo that phase change, the heat of fusion in this case. So the same mass times that constant. This constant, this constant, this constant, this constant would have to be given. But then that ice, after it has melted, is now liquid water at 0. That liquid water at 0 is going to warm up. So then we've got all of these numbers to put together. This is one that you could either solve in your calculator or do the math. Obviously, we would want to be able to do it either way, but it'd be quicker if we used an equation solver. But we're trying to just figure out, once again, that the X is the same in both cases. That mixture is all just liquid water after the ice has melted. It doesn't matter that some started as ice and some started as water. And we would likely project that it would be fairly cold water. Obviously, the temperature has to be between 0 and 20. Projecting beyond that, even for me, is fairly difficult. But because the water was so much more in mass than the ice, we are able to predict somewhat that will end with liquid water. If I had a 200-gram piece of ice and only 25 grams of water, we might expect that water actually cools down and maybe even some of it starts to freeze, or that we end very, very close to that 0. So that's important, because although we don't always recognize that, ice can be much colder than 0, and that ice that's colder than 0 would take even more heat away from the water and could, given the right amount of heat transfer, cause some of our liquid water to freeze. And then on part D, just a different heating curve. We have a melting and a boiling point here. The melting point is slightly above 80, because right down here we've got solid, we've got liquid, we've got gas, and this is ammonia. The boiling point is right there. It's somewhere between -20 and -40. I believe I've read the graph correct, that it's around -35. And we would just need to be able to read a graph, especially read the negatives there. The greatest specific heat means which one takes the most energy to change the temperature. So it's actually going to be the flattest section, which is why the solid is correct. It's the least steep, or the most energy is required to change that temperature. At the molecular level, why does specific heat vary? And this is true for ammonia, for water, for everything. You're never going to see all 3 sections with the exact same slope. It has to do with, for that specific substance, how strong are the intermolecular forces between the particles? Maybe in the solid state, how neatly arranged are the particles? Maybe in the liquid state, how close together are the particles, or how dense is the liquid state compared to the solid state? And then in the gaseous state, the particles are very far apart. So as we're heating it up, they're already moving fast, but it is difficult to transfer heat or transfer kinetic energy and speed from one particle to the next. But it's all about strength of attractions, distance between particles, because when we are looking at changes in temperature, we are looking at changes in average kinetic energy between our molecules.